All right, guys, so today we're going to talk about special parallelograms. So remember, everything we're talking about today, still a parallelogram, right? So that means it's going to have all 5 of those properties that we talked about yesterday, right? So let's review them really quick. If it's a parallelogram, it has opposite parallel sides. It has congruent opposite sides. It has congruent opposite angles. It has consecutive angles that are supplementary, right, because they're same side interiors, and it has diagonals that bisect each other. Okay, so we're going to be talking about rhombuses, rectangles, and squares today, and they're all parallelograms, so they have those 5 properties, but they're more specialized parallelograms, so they have additional properties that belong just to them. Okay, so that's what we're going to talk about. All right, so we're going to start by just defining what a rhombus is. Okay, so you guys know these shapes, right? So a rhombus is a parallelogram with 4 congruent sides. Again, I'm going to try to go through this pretty quickly, so feel free to pause or rewind if you need to. All right, so if I'm labeling my picture, 4 congruent sides, right? That is the defining characteristic of a rhombus, right? It's a parallelogram with 4 congruent sides. Okay, moving on. A rectangle, of course, is a parallelogram with 4 right angles. A lot of people, when they think about defining a rectangle, they think they're like, oh, well, opposite sides are congruent, right? But that's true of any parallelogram, right? Not just rectangles, right? So the defining characteristic of a rectangle is that it is a parallelogram, but in addition to all those 5 properties from yesterday, they have 4 right angles. Okay, so everybody's a right angle. All right, and then lastly, we have squares, and of course, squares have both of those properties that rhombuses and rectangles do, right? They have 4 congruent sides and 4 right angles. All right, so I'm going to sketch all that in my picture. All right, so there's my 4 congruent sides. Here's my 4 right angles. All right, so therefore, oopsies, we can say that, it's a tiny little right angle, therefore we can say that all squares are rhombuses. You can say rhombi if you want, and rectangles. So this is where we kind of start getting into those statements when people say all squares are rectangles, which is totally true because all squares have 4 right angles. But the statement all rectangles are squares is not true because not all rectangles have 4 congruent sides, right? So all rectangles are squares, but not all squares are rectangles, right? So you need to be able to kind of understand that kind of statement. And the reason why is because your favorite always sometimes never questions, right? Are making their comeback here in Unit 6. So we're going to look at these statements and see if they're always, sometimes, or never true. Remember, the hypothesis, the if part, that's always true, right? That's what we're looking at. And then you're asking yourself, is this conclusion always, sometimes, or never true? Okay, so here we go. If a quadrilateral is a rectangle, then it is a parallelogram. Okay, well, if I'm looking at a rectangle, then yeah, I'm totally looking at a parallelogram, right? That is always true. All right, number 2, if a quadrilateral is a parallelogram, then it is a rhombus. Okay, well, that's only sometimes true, right? Because parallelograms now can branch out into rhombuses, rectangles, and squares. So just because I'm looking at a parallelogram doesn't mean it has to be a rhombus, right? It could be a rectangle, right? So this would be sometimes because there's other shapes it could be. All right, number 3, if a quadrilateral is a square, then it is a rhombus. All right, well, remember, I'm going to kind of draw a picture. If I'm looking at a square, right, square is very specific. It has to have 4 congruent sides and 4 right angles. So if I'm looking at a square, am I looking at a rhombus? Yes, right, because all squares are rhombuses. So this is always true. All right, I want you to think about this next one really quick. If a quadrilateral is a rectangle, then it is a rhombus. If I'm looking at a rectangle, then I'm looking at a rhombus. What do you think about that? So the answer is sometimes, right? And you might be thinking, what? Why is that sometimes, right? It all has to do with this hypothesis, right? If a quadrilateral is a rectangle, well, I'm going to ask myself, what could that be? If I'm looking at a rectangle, then that means I could either be looking at a rectangle or I could be looking at a square, because all squares are rectangles. So when someone tells me I'm looking at a rectangle, it could be a rectangle or a square. And then when someone says I'm looking at a rhombus, well, that could actually be a rhombus, or I could be looking at a square, because all squares are rhombuses. So the only time this statement would be true is if I'm looking at a square, which is both a rectangle and a rhombus, right? And so that would be the sometimes, right? If I'm not looking at a square, then it's not true, right? But that's why our answer is sometimes. It's either a square or it's never, right? So that's why sometimes is our answer there. That one's kind of tricky. All right, the last one is if a quadrilateral is a square, then it is a rectangle. Well, again, a square is the most, let me draw it above. I'll draw below. A square is the most specific parallelogram you can draw, right? So if I'm looking at a square, am I looking at a rectangle? Yes, always, right? Because all squares are rectangles, right? So you have a lot on your homework today. You have a lot of always, sometimes, nevers and true, false statements, right? So you really want to kind of focus on that hypothesis and ask yourself, what kind of shapes could I be looking at that would make this hypothesis true? All right, so just like yesterday, because we are doing proofs today, this is our last day of proofs, we need some proof statements. So we're basically taking those properties or those definitions that we just learned, and we have these corollaries. Now again, just like yesterday, you're not allowed to actually use corollary or theorems or whatever in your proofs. You have to write the if-then. But this corollary is written as a quadrilateral is a rhombus if and only if it has four congruent sides. And if you remember, if and only if is a biconditional, and a biconditional statement is true forwards and backwards, which means it is totally up to you in a proof to figure out, do I want to use this statement forwards or do I want to use it backwards? So do you remember yesterday when we had the statement, if parallelogram, then four congruent, if parallelogram, then opposite sides parallel. And then we had, if opposite sides parallel, then parallelogram, right? And which one we used in our proof depended on what we were trying to prove, right? Same thing here. So I'm just going to actually split this up, right? So if I write it forwards, it would be if rhombus. And unfortunately, I really don't want you trying to draw a rhombus. Parallelograms are really the only ones that you should be drawing. If it's a rhombus, a square, or a rectangle, you need to actually write the word out because no one would be able to really tell the difference between them. So if rhombus, then four congruent sides, right? And I would use that one if I already knew it was a rhombus. Or you could say if four congruent sides, then rhombus. And I would use it backwards in that order if I was trying to prove that the shape I was looking at was a rhombus, right? So that's going to be up to you to determine which one of those you use. Same as yesterday, no big deal. All right, and we have that same corollary for the rest of these guys, right? If a quadrilateral is a rectangle, or a quadrilateral is a rectangle, if and only if it has four right angles. Okay, so that means I'm going to either use if rectangle, then four right angles, right? Or we're going to use if four right angles, then rectangle. All right. And lastly, with the square corollary, right? A quadrilateral is a square if and only if it has both four congruent sides and four right angles. So you guessed it. Here we go. If square, then four congruent sides and 4 right angles, or if 4 congruent sides, then, I'm sorry, I forgot the and. There you go. And 4 right angles, then square. All right, and we're going to do some proofs here in just a little bit, so you'll kind of see how we're going to be using those. All right, so if you listen to any part of the notes today, this is the part I need you to really pay attention to, because there are other additional properties of rectangles that just happen because of all the different stuff that's happening inside of the rectangle, okay? So in the little green bubble here, hold on, I'm trying to pick a color. So in the green bubble, we have the main property of rectangles, right? And that is a parallelogram is a rectangle if and only if the diagonals are what? Now yesterday, remember, you don't write this down, I'm just going to draw on here. Yesterday we were doing parallelograms. And parallelograms are like rectangles that have been pushed over, like someone's like shoved it over. So in a rectangle, in a parallelogram, because it's slanted, you always have one long diagonal and one short diagonal, right? The long diagonal going in the direction of the slant, right? But in a rectangle, right, that parallelogram has been pulled perfectly perpendicular to the ground, right? So now when I draw his diagonals, right, they're going to be perfectly congruent to one another because my shape isn't tilted to the side anymore. Any shape that's tilted will never have congruent diagonals, right? But rectangles, they're not tilted anymore. They're perfectly perpendicular. So we have diagonals that are congruent. All right. And I'm going to label these. I'm just going to kind of label this rectangle A, B, C, D so I can use those angles or those vertices, right? And so this is telling me that diagonal AC is congruent to diagonal BD. Okay? Now, while I need you to understand that concept, I also need to, I'm going to kind of zoom into my picture here. I need you to understand that there is a ton of other naturally occurring properties that happen inside of this rectangle besides just the diagonals being congruent. So first of all, I just want to point out that all of our angles, of course, are right angles, right? So this is a right angle. And so does everybody see that? I'm going to kind of highlight. Hold on, give me one sec. Let me increase the size of my highlighter there. Okay. Does everybody see by just looking at one diagonal? Oh my goodness. I'm sorry. I want to use the highlighter, not the actual yellow marker there. There we go. That's better. So do you see by just looking at one diagonal, like AC, that he's actually the hypotenuse of right triangle ADC, right? And there's a lot of right triangles happening in this picture. So you need to be aware that that's going on. I'm so sorry. Let me try. Oh my goodness. Sorry. I enlarged the wrong thing. Oh my goodness. Okay. There we go. I'm good. All right. So inside of every rectangle, we're going to have right triangles. Well, that's important because we just got done taking a test over right triangles, right? Which means everything that we learned about right triangles is going to be up for grabs on a rectangle problem, right? And by that, I mean Pythagorean theorem. You might need to use Pythagorean theorem to solve for missing parts of a rectangle. You might need to use special right triangles, right? Your 45, 45, 90s or 30, 60, 90s. Or you might need to use trig to solve for missing parts of rectangles, right? Especially like missing angles and stuff like that. Okay, so the fact that there's right triangles inside of rectangles means all of that is up for grabs. Notice I didn't put geometric mean in that because we're not going to be using geometric mean anymore because we're not drawing altitudes, to the hypotenuses and all that kind of stuff. All right, something else. We're not done. Something else we need to talk about with these diagonals. So not only are the diagonals congruent, but remember, he is a parallelogram, and the diagonals bisect each other. So if they bisect and they're congruent, doesn't that mean, obviously, we know that the two halves are congruent because the diagonals bisect each other, but if they're congruent, that means they bisect each other and all four of those pieces are congruent. And if all four of those pieces are congruent, then do you happen to notice what other kinds of triangles are inside of rectangles? Let me get a gray marker. All right, hopefully you guessed it. Right, isosceles triangles. Isosceles triangles, right? And so you can see that there's two different pairs of congruent isosceles triangles, right? I'm gonna just be scribbling a lot. Clearly the one on the left is also congruent to the one on the right. We can prove that with side, side, side. And the isosceles triangle on the top is congruent to the isosceles triangle on the bottom, right? And so we have two pairs of congruent isosceles triangles. And so don't forget, what's the main thing we know about isosceles triangles? They have congruent base angles, right? The good old base angles theorem. So I'm going to kind of draw that in my picture, right? So I know this angle is congruent to this one, which of course means this base angle is congruent to this one, right? Because those are isosceles triangles. All right, and then I know, let's see how many different colors I can use here, right? Then that means this base angle is congruent to this one, and that's congruent to this one and this one, right? So I have four congruent pairs of base angles, or four congruent base angles, right, for those, the top and bottom isosceles triangles. And then, of course, I know these two non-congruent angles have to add up to 90. Right, so there's so much going on inside of a rectangle, right, that we have to keep all that in mind as we work with them, okay? All right, that was a lot of talking for just that little bit there. All right, let's go talk about rhombuses. All right, so rhombuses actually have two special properties that we're going to write down, and they're both about their diagonals. Now, rhombuses are still tilted like regular parallelograms, so their diagonals are not going to be congruent, right? This diagonal is always going to be longer than this one, right? Because he's tilted to the right. So the right diagonal, right, the one going from bottom left to top right, will always be longer, right? So the diagonals are definitely not congruent, but there is something special happening with their diagonals. And that is, well, let's prove it really quick. You don't have to write all this down if you don't want to. You can just listen. So we already know that, right? We already know all four sides are congruent. We also know all the opposite sides are parallel, right? Which means this angle is congruent to this one, right? And we also know that we can tell, we can prove actually in our picture, right? Well, here, I'll do this. Again, don't write any of this down. I'm gonna erase all of this. I'm just scribbling all over my paper, right? So don't we kind of have this going on, right? So I can totally prove that this triangle and this triangle are congruent by AAS, right? But then in a because all of my angles are congruent, because all of my sides are congruent, I also know that this diagonal is acting as a line of symmetry, right? Does everybody see if you kind of tilt your iPad, right? If you're looking at it like this, right? It's a perfect symmetric figure, which tells me that this angle is also congruent to that one, right? And that means this angle has to be congruent to that one, and this angle has to be congruent to that one, right? So all four of these triangles are actually congruent to each other, right? It's 4 congruent triangles. Now that, I'm going to erase all this mess. There we go. So now what does that mean? Okay, hold on. Let me redraw my diagonals. I didn't mean to erase those. So because all 4 of these triangles are congruent, I have these 4 angles in the middle, and they're all congruent. Well, if I go full circle, that means all of those angles have to add up to 360 degrees. Well, if they're all congruent, then 360 divided evenly amongst 4 angles is 90 degrees, right? And so that means that the diagonals are perpendicular. Okay, and that is a big perpendicular. All right, and that is a super big property of rhombuses. And guys, that is not going to, that right angle box is never going to be there for you, right? You have to know that that property is there so that you add the right angle box, okay? And then, of course, because that's a right angle, that means you have 4 congruent right triangles. I'm going to kind of write that down. All right. So we have 4 congruent right triangles inside of every rhombus. And the fact that they're right triangles means that Pythagorean theorem and special right triangles and trigonometry, all that math is on the table for a rhombus because they contain right triangles. So we're right back to Unit 5. Another thing you want to notice is if I put my congruency marks on the legs, sorry, my brain is tired. If I put my congruency marks on the sides, because rhombuses have 4 congruent sides, do you guys see how this, if I look at this whole half of a rhombus, right, it's an isosceles triangle, right? So there's just so much happening here, right? I'm just going to kind of put isosceles. I don't know why I'm writing in yellow. That's kind of hard to see, right? Isosceles triangles on each half of the rhombus, which again kind of proves our next statement, right? I'm going to get a little ahead of myself, but doesn't that mean these are also congruent base angles? And that's a line of symmetry, or those are congruent isosceles triangles. So those are congruent base angles, and all 4 base angles are congruent to each other. And that leads us to the second property that says if it's a rhombus, that the diagonals bisect each pair of opposite angles. So that's saying that when you draw a diagonal, it's automatically going to bisect the angles. And that should make sense because all the sides are congruent, which means this is a line of symmetry. This is going to happen on any figure that has 4 congruent sides, right? Anything that has 4 congruent sides is going to be symmetric, right? And so that line of symmetry is telling me that the angles are being cut in half. Another way you might see this worded, I'm going to write this off to the side here. I'm going to put a little asterisk here. Diagonals bisect their respective angles. And what that means is, like, when I'm talking about, let me get a highlighter here. When I'm talking about this diagonal, I'm talking, these are his respective angles because those are the angles that that diagonal hits. I'm telling you this because that's the verbiage that's on your quiz over this stuff. It says, you know, true or false, or always, sometimes, nevers, or whatever, that diagonals bisect their respective angles. And that's what that means. Respective just means the angles that they're touching. Okay. And then, of course, there's another diagonal. So I can draw him. Oh, my goodness. I can draw that diagonal, and I know that's also a line of symmetry, and so it's bisecting his respective angles. Okay, and again, we just talked about how that has to be true because I have isosceles triangles on each half, and those are base angles of those isosceles triangles. Right, so there's just so many properties, again, happening here that if you happen to forget them, you should still be able to come up with these relationships because it's all stuff that we have already learned, right? And we can prove these relationships very easily, okay? All right, that's a lot of stuff. We didn't even write down a whole lot, but that's a lot to think about. All right, so we have rectangles that have diagonals that are congruent, again, only because they're perpendicular. The sides are perpendicular to the ground. Rhombuses that have perpendicular diagonals and bisecting angles. Okay. Now squares, of course, have all of these properties because squares are both rectangles and rhombuses. So everything we just talked about totally applies to all squares. Okay. All right. Let's go work a couple of problems. See how we're doing with our math here. All right, so we're talking about a rectangle, WXYZ, the diagonals intersect at O, and it says, given that the measure of WYX is 56, that's already been labeled for you, and WY is 33. Okay, that's going to be a little more difficult to label here, so I'm just going to kind of highlight it. All right, so that's 33, that whole thing. Okay, find the following. Okay. So the measure of angle ZOY. Okay, ZOY. Okay, so that's this angle here. All right. Well, let's see. We know that it's a rectangle, so we know this is a right angle. So if that's a 56-degree angle, right, then we know that this is what, 34 degrees right here? But we also know that the diagonals of a rectangle are congruent. So all four of these pieces of the diagonals are congruent, which means we have an isosceles triangle right here, which means his congruent base angle would be 34 degrees. And now I can analyze this triangle that's going on right here. And I could use my triangle sum theorem. Now, this is not the only way to do this problem, right? I'm just kind of talking through what my brain does first, right? You might see a totally different relationship, which we'll talk more about some in just a second. So let's see, that adds up to 68 degrees, right? And so it looks like that's going to leave us with 112 degrees. Let me write that in. Then that means this should be 112 degrees for that angle ZOY. Okay. All right, what about angle XOY? Okay, that's this guy right here. Well, XOY is just the linear pair to ZOY that we just found, so he must be 68. And another really cool way to think about this, I don't know if y'all remember this, but do you guys back in unit 3, we talked about exterior angles. So if I'm looking at this triangle and I extend this side, 68 would be the exterior angle, and he's equal to the sum of the two remote interior angles. So I actually would have known that that was 68 without ever having to find that 112 degree angle, right? So you can use that relationship too. So I'm just bringing that up in case you remember that. All right, next up is solving for the length of side XO, or this guy right here, XO. Well, if the whole diagonal is 33 and the diagonals cut each other in half, well, then the 33 is going to get cut in half, right? So I know that each one of these pieces is 16.5, right? Each one is 16 and a half because the diagonals are both 33 units long, right? So 16.5. All right. Then we need to solve for XY. Let me change colors here. So XY being this side. Well, that's not a diagonal, and yeah, but it is the side of a right triangle, right? I'm going to kind of redraw that down here in case anybody needs that. This is my right triangle. Not that. Thank you, Notability. There we go. That's better. So here's that right angle. Here's x, y. Here's z over here. I do know that this is 33, right? The diagonal. And I know that this is 34 degrees. And I know that this is 56 degrees, right? And I'm looking for x, y. Question mark. Well, looks like the only way I'm going to be able to solve that is trigonometry, right? Because that is a missing side of a right triangle. I can't do Pythagorean theorem. It's not a special right triangle. I definitely want to check for those things first, right? So I'm going to solve for this. I'm going to put a lowercase x. And so let's see, depending on which angle I choose, I'm going to use the 34-degree angle. So that would make x the opposite and 33 the hypotenuse. So I'm going to use sine. So the sine of 34 equals opposite over hypotenuse. If you want to use the 56-degree angle, that's cool, but you would just use cosine since x would be the adjacent to him. You'd get the same answer. So we're going to multiply both sides by 33. And again, the downside of trig is that's my exact answer, right? So the length of xy is 33 sine 34, which doesn't really mean a whole lot to us, right? So we are going to type it into our calculator. And I'm going to get the approximation, and it's about 18.5. Okay? So just be able to use all of that math knowledge that we have, right, to solve for any missing parts there. All right, moving along. Example number 2. We've got a rhombus. Answer each question. Okay. Let's see. The measure of BAE. Okay, BAE. So 32. So I'm going to label that. Find the measure of BCE. BCE. So we're looking for this guy right here. Well, remember, if I were you, anytime I see a rhombus, I'm going to kind of go to town with my markings, right? Because I know, first of all, that the sides are congruent. So I'm going to put those in. And I also don't want to forget that the diagonals are perpendicular. So I have 4 congruent right angles. And both of my diagonals are lines of symmetry, which means the 4 angles that lie along this angle are congruent, and the 4 angles that lie along this angle are congruent. Well, and as long as I know my markings, then I just answered my question, right? Then the measure of angle BCE is 32 degrees also. So the measure of angle BCE is 32. And that, of course, makes sense because those are also base angles of this isosceles triangle right here. All right. Let's see. EDC is 43. Okay, so EDC is 43. Which means all of these angles along that diagonal are 43 degrees. And it says find the measure of angle CBA. Well, that's the whole angle, right? And I know that each one of these is 43 degrees. So therefore, the measure of angle CBA is 86 degrees. Awesome. Okay, next up. It says the measure of angle BEC. Okay, BEC. Ooh, that looks like our right angle, right? That's where our diagonals are coming together there in the middle. Is 3x minus 5. Solve for x. Okay, well, 3x minus 5 has to equal 90. Again, those right angle boxes are not going to be there for you, right? You're going to have to remember that on your own, right? And so we add the 15. We get 105. And what's that going to give us? 35. Looks good to me. All right, and then last but not least, it says if ADE, okay, so let's look at that. So ADE is this guy, I'm just gonna put a dot there, is 5x minus 8, and CBE, so that's this right here, is 3x plus 24, solve for x. Well, okay, we've already, and again, these are totally independent questions, right? We're not going to use that 43 degrees again, right? These are independent questions, like totally brand new rhombuses each time. So we know that those are both 40, I'm sorry, I just said that. We know that both of those are congruent angles, not only because they're alternate interior, right? But because in a rhombus, all 4 of those angles along the diagonal are going to be congruent. So we just simply need to set 5x minus 8 equal to 3x plus 24. All right, so we're going to solve that. So 2x equals 32, so x equals 16. All right, let me go erase those giant pink dots that I put in there. All right, last question. If the measure of angle BAD, use orange, so BAD, so that's this whole angle, is 4x plus 14, and ABC, so that's this whole angle, solve for x. Okay, well, what do we know about this whole angle and this whole angle? Well, we know that it's a parallelogram, right? And so they have to be supplementary, right? A rhombus is still a parallelogram, so all those properties from yesterday hold true. So since angle A and B are consecutive angles, they must be supplementary. Right, so we can just simply add, if everyone's cool, I'm going to go ahead and combine like terms. 6x plus 24 if we add up our like terms, and we know that has to equal 180 degrees. Okay, and then just subtract our 24. Right, and then divide by 6, and we should get 26. Okay, so just using properties of a rhombus and or just parallelograms in general. Okay. All right, example 3. Sorry, we're close. All right, example number 3, we're going to do another coordinate proof. Okay, so we did one yesterday, but we were kind of taking baby steps with the graph, but now we don't have a graph anymore. So it says complete the coordinate proof, keep work neat and organized. Without using graph paper, classify the quadrilateral. All right, so notice they're just telling us it's a quadrilateral. So I don't really know if it's a parallelogram, a rhombus, a rectangle, or a square. And that's all we've learned up to this point. So it's going to be one of those 4 things, or maybe it's not none of the above. Maybe it's just a weird quadrilateral. Who knows? Now, I'm not opposed to you sketching a graph just to kind of see where A, B, C, and D lie in relation to one another, but you cannot use that in your proof, right? You're just using that as kind of a visual. So let's see if I'm just eyeballing. That line is super crooked. You know, I can't live with that. Okay, here we go. All right. So let's see, negative 3, 4. Again, I'm just kind of eyeballing. It doesn't have to be perfect. So let's say A is hanging out there-ish. B is at 0, 6. So let's say up here. C is at 2, 3. 2, 3. So let's say it's about there. And D is at -1, -1. Again, it doesn't have to be perfect. I'm totally just sketching that to give myself a visual of where the points are relative to one another. That doesn't even look like a good shape at all. But again, I don't care. I'm just kind of seeing who's opposite from who and kind of where they are. All right, so we're going to have to do some coordinate math. So remember what we did yesterday. That either means distance formula. You can use slope, right? So you can kind of do whatever you want. I'm going to start off with distance formula here. You don't have to, right? I'm just going to do all my segments, okay? So here we go. I'm just going to run through this really quickly. So here we go. The length of AB. All right, big old distance formula. Big square root. All right, so I'm just using these 2 coordinates for AB. So x minus x squared plus y minus y squared. So here we go. 0 minus -3, which will change into a plus sign, and then 6 minus 4 squared. All right, so I'm going to clean that up. That's going to give me 3 squared is 9 plus, I forgot my little parenthesis there. 2 squared is 4, and that's going to give me the square root of 13. Okay. I'm going to go ahead and do, you can just go around, or you can do the opposite side from AB, or the consecutive side to AB. It really doesn't matter. I'm just going to go ahead and just travel around. I'll just do BC next. I'm just going to go clockwise around. All right, so here we go. Now I'm going to be using BC. So I'm using these points here. All right, here we go. X minus x squared plus y minus y squared. Again, the order does not matter in distance formula because you're going to square it anyway. So let's see. 2 squared is 4. Negative 3 squared is positive 9. Oh, what do you know? 13. Square root of 13. So far, A, B, and BC are congruent. Right? Now, you can't stop there because I don't know this is a parallelogram yet. It just says quadrilateral. So I got to keep going. So I'm going to do CD. Just going around. So CD. Okay, now I'm using these two guys. All right, so negative 1 minus 2 squared plus 1 minus 3 squared. Again, it's a very quick formula once you get going. So negative 1 minus 2 is negative 3. Negative 3 squared is 9. Plus 1 minus 3 is negative 2, but negative 2 squared is positive 4. Crazy. Another square root of 13. All right. So far so good, but we're not done. Now I have to do the very last one, which is DA or AD. It doesn't matter what order you put those in. And yes, you must do the fourth. Right? Because I can draw a quadrilateral that has 3 congruent sides, but not a 4th congruent side, right? So you do have to keep going. So here we go, DA. So I'm using these two now with my distance formula. So negative 1 plus 3, because the double negative, plus 1 minus 4 squared. All right, so that's going to give me 2 squared, which is 4, and negative 3 squared. Oh my goodness. All right, so looky there, right? We did distance formula for all 4 sides, and then you need to conclude, you need to write down what you just found out, right? Don't expect your reader to do that, right? It's a proof, so you're still technically explaining and baby stepping it as you go, right? So we've just proven that all sides are congruent. All sides congruent. Yay! All right. So that means it has to be what, right? If all the sides are congruent, it has to be a rhombus, or it has to be a square, right? So we've narrowed it down. It's not a rectangle. It's not a parallelogram. Well, it's not a plain old parallelogram, right? It either has to be a rhombus or a square. So we are not done. So we need to figure out if this is a rhombus or a square. And there's quite a few ways you can do that, right? So let me go back up here really quick. So you can do one of two things. Let's see. The differences between rhombuses and squares are kind of going to be the differences with the diagonals between rhombuses and rectangles, right? So in a square, because all squares are rectangles, the diagonals have to be congruent. In a rhombus, the diagonals will not be congruent because he's tilted, so he's stretched more in one way than the other. So if you wanted to, you could do 2 more distance formulas with the diagonals and see if they're congruent or not. Or the other defining characteristic between a rhombus and a square is that squares have to have 4 right angles and rhombuses don't. So you could figure out if the sides are perpendicular to one another or not, right? And so what do we know about perpendicular lines? Well, they have opposite reciprocal slopes, right? So you could do a quick slope calculation and see if they're opposite reciprocals or not. If they are, square. If they're not, rhombus. Okay, so just to practice that skill, I'm going to do it that way. You could do the diagonals, though, if you want to. That would be the same end game, right? So I'm going to analyze the slopes next. Okay, so I'm going to just do, and you don't have to do all the slopes, right? You just have to find one corner, right? Because we know that this is a parallelogram for sure, because the opposite sides are congruent. They're just all congruent, right? And so once I just find one corner, right here, let me just draw a picture instead of trying to sit here and explain it verbally, right? If I just find one right angle, then I automatically know all the other angles have to be right angles, because I know the opposite angles are congruent in a parallelogram. And I know that the consecutive angles are supplementary, which means his little neighboring buddies have to be right angles. So you don't have to sit there and find all the slopes. You just have to find one corner and see if they are perpendicular or not. Okay? Because we've already proven that it's definitely a parallelogram of some kind. We just have to be as specific as possible. So I'm just going to do the slope of AB and BC. I'm just choosing that corner, not for any reason, right? But I'm going to choose that corner. So I'm going to go find the slope of AB. So I'm going to do my y2 minus y1 over x2 minus x1, right? So 6 minus 4 and 0 plus 3. All right, so that's going to give me 2/3 for the slope of AB. All right, and then I'm going to go find the slope of BC. Again, I'm labeling all my work so nobody has to guess what I'm doing. So BC, change in y's, so 3 minus 6, 2 minus 0, and that gives me -3/2. Are those opposite reciprocal slopes? I think so. So we have just proven that side AB is in fact perpendicular to side BC. And if you want to, I'm just going to write this for note purposes, right? Opposite reciprocal slopes. So if that corner is a right angle, everybody's a right angle, which means this is a square. And you have to be specific, right? You have to keep working until you have narrowed it down to the most specific shape that you can, right? And so there you have it. This must be a square. Okay, tomorrow we'll add kites and trapezoids to the mix. All right, last one, and then we're going to do a couple of proofs and we'll be done. All right, so notice this picture. There's a lot going on. It wants us to find all these crazy missing angles. So I don't really like to go one at a time. I'm just really going to go to my picture, and I'm just going to label every possible angle in my picture, and then I can just transfer that to the angles over there on the right-hand side. So the crazy thing about this picture, if you read the directions, it tells you that it's a rectangle with a rhombus sitting on top, right? So so this is a rectangle, right? All right, so I'm just gonna focus on the rectangle for right now. I'll get to the rhombus in just a second. All right, so I'm gonna label every single angle inside of this rectangle. Well, I'm gonna start here. Oh, goodness, sorry y'all. I'm gonna start here because I know rectangles have 90-degree angles, right? So that obviously means that this guy is going to be 27 degrees next to him. But I also know that the diagonals are congruent. So I'm making this whole slew of isosceles triangles, which means this is 63. And the base angles over here are all 63, right? Because those are this and this. Those are congruent isosceles triangles. And if that top right corner is 27, then his congruent base angles are all 27. Ta-da! And then I can either use the exterior angles theorem like I was talking about before, or I can just do a quick little triangle sum theorem. I've got 63 and 63, that's 126 degrees, right? And if I have 126 degrees inside of my triangle, then that leaves 54 degrees there in the center. And if that's 54, then his vertical angle is 54. And then that means this is 126 because, and I'm doing the whole angle. I'll split it here in just one sec. All right, so look at all those pretty angles, right? All done. Okay. All right, now we have a rhombus. Let me take that down a notch. We have a rhombus here, sitting atop and inside our rectangle. Well, remember, rhombuses have 4 congruent sides, right? So these sides are congruent to the other 2 sides, which means all my diagonals are lines of symmetry, right? And if I have 27-degree angles here and here, well, then these have to be 27 degrees because the congruent base angles, because the angles are being bisected by the diagonals, right? We can just prove that a million different ways. And then I know this other diagonal right here is bisecting the angles. So that 126 is being split in half. So I know this is 63 and 63 because that 126 right there is being split. And then don't forget, of course, that the diagonals are perpendicular to each other. So all these guys here in the middle are 90 degrees. Look at that. Look at all these crazy angles, right? But now that I have everything labeled, I can just transfer that information over here to my little blanks over here. So I'm just going to do that really quick, right? So GDB 27, DAB 126, it's the angle at the very top, GCE 126, AHB 90, right? That's in the middle of our rhombus. And then we have ABC, which is 54. BCG, also 54. DEG, 90, right? That's one of the corners of our rectangle. And DGB, 63. All right. Next up, proofs. All right, we're just going to do 2 quick proofs and then we're finished, you guys. So we're going to do one for a rhombus and one for a rectangle, just so you can kind of see how this plays out. Okay? All right, so proof number 1, we're trying to prove that ABCD is a rhombus. Okay, it certainly looks like a rhombus, right? But we're going to prove that. Okay, so here we go. I'm going to be lazy. I'm going to copy all of this. I'm just going to put it in my statements box, and I'm gonna put this in there too. There we go. All right, and then my given. I feel very lazy when I do this. That's okay. All right, so there's our step 1, right? Our givens. So the cool thing about the given, what's super important, is that they're telling us that this is a parallelogram. So we know all the properties of parallelograms are holding true. Now, we're probably not going to need all of the properties, right? We don't want to sit there and just start listing them in our proof. We want to pick the ones that are going to help us prove this is a rhombus. Okay? All right. So I'm going to go look at the other given, and they're telling me that ADE, angle ADE, so that's this angle, is congruent to angle ABE, which is this angle. All right. So how is this going to help us prove that this is a rhombus? Well, the defining characteristic of a rhombus is that it has 4 congruent sides, right? And that's really the only if-then statement that we've written down, basically, other than the properties at the, about the diagonals. But the one thing that jumps out at me, I don't know about you guys, is that when I'm looking at this picture, I'm seeing an isosceles triangle. Because I have the given told me that those 2 angles are congruent, and those are base angles of that triangle that I just highlighted in orange. Which means I can then state that if I have 2 congruent angles, then I must have an isosceles triangle, and these 2 sides must be congruent. So I can say AB is congruent to AD, And hopefully you remember this, right? If your base angles are congruent, then the opposite sides from those base angles are congruent, right? And that is the isosceles triangle converse theorem, or the base angles converse theorem, if you want to use that one. All right. Well, that's pretty awesome that I have two consecutive sides that are congruent, because I also know, and I haven't used this yet, right? I've used that given up, right, to get me this piece of information. But I haven't really done anything with knowing that it's a parallelogram yet, right? Because I wanted to kind of see which property of parallelograms I actually wanted to use. Well, now it should be pretty clear, right? They've given me, I now know information about the sides. And what else do I know about the sides of parallelogram? Well, opposite sides are congruent, right? So no matter what markings I put in this picture, I can underline that, I totally can prove that AB has to be congruent to his opposite side, right? CD. And I know that AD must be congruent to CB. And I know this because of yesterday, right? If parallelogram, right? Because they told me that in the given. If parallelogram, then opposite sides are congruent. Well, now you notice we have a couple of little repeaters happening, right? We've got an AB in step 2, and we also have an AB in step 3. And we have an AD in step 2, and we also have an AD in step 3. So if these two guys are congruent, then that means, and you see them right here, then that means these two guys must also be congruent, right? So everybody has to be congruent, right? And hopefully that makes perfect sense, especially when you're labeling it, right? Because if I know A, B, and C, D are congruent, well, then of course I'm just going to put one hash mark. And if AD is congruent to BC, then I'm going to use one hash mark. So everybody has one hash mark. So all four sides are congruent, and that is the defining definition of a rhombus. Now, we just can't say it's a rhombus yet, because we actually have to make the connection that all four sides are congruent to each other. And we can do that. So it's going to look kind of weird, but I literally have to say that AB is congruent to CD, is congruent to AD, is congruent to CB. I have to string them all together and say that all four are congruent. And I do that because I have this middleman that's connecting these guys to these guys, right? And so you might have guessed it, that would be the transitive property of congruence. Congruent, 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 right? It's a whole train of congruencies connecting each other. Okay, so transitive property, and that's when you're like, oh, all four sides are congruent. Yay, that means that ABCD is a rhombus. ABCD is a rhombus. And please, again, spell out the word rhombus. Don't try to draw a rhombus, right? The only shape I'm allowing you to do that with is parallelograms and triangles, right? Other than that, you need to write the word out. And I know that because, remember, I'm going to go way back up here. Remember our rhombus corollaries. So I'm either going to use if rhombus, then four congruent sides, or if four congruent sides, then rhombus. So which one are we going to use? Well, we don't know it's a rhombus yet until we prove it, right? But we have proven we have four congruent sides. So that is our hypothesis. So if four congruent sides, because that's what we just proved, then it must be a rhombus. And there you have it. Little arrow here. Okay, so that's our proof for a rhombus. Again, they can vary a lot, but that's kind of the gist. All right, let's go do one more. This is proving that this is a rectangle. Okay, so again, give me a second. I'm going to copy and paste all my givens here. There's lots of information, which is good. The more information, usually the easier the proof's going to be. All right. And I'm going to label that box number 1. Again, feel free to pause the video if you need to. I'm going to go ahead and hop right into this. So I'm going to start marking my givens and get a kind of game plan going in my head. So TR, that's this guy, is congruent to CE. Okay. And angle RCE, so that's this angle, is congruent to TRC. Okay. And then triangle TRE. Let's see if I can kind of do some highlighting. TRE, so this triangle, right, is congruent to RCE. So this triangle. Oh, let me overlap a little. I'll do blue. Here we go. All right, that's a lot going on in that picture. You don't have to do all that if you don't want to. Okay. Well, there is a big difference between this problem and the last proof, and that is up here, they told us it was a parallelogram. And that gave us a lot of leeway because we knew all those properties were already holding true, right? We don't have that going on in this one, right? They haven't told me that this is a parallelogram. So if I want to prove something's a rectangle, I probably need to prove it's a parallelogram first, right? Because rectangles are not the only things that have right angles, and they're not the only things that have congruent diagonals, right? Other shapes have those things too, right? So we want to make sure it's a parallelogram first and foremost, and then from there we can prove that it's a more specific rectangle. Okay, so let's look at what we have here. This is pretty easy to prove that this is a parallelogram because we can, of course, use the given that these two angles, which are alternate interior angles, right, that those are congruent. So therefore, that means we must have parallel lines. And the parallel lines, again, look for the Z shape, right? There's our Z shape right there that are creating those alternate interior angles, which means that not only are TR and CE congruent, but they're also parallel. And again, there's more than one way to do this. I'm just trying to find the most, efficient way to prove that this is a parallelogram. So I'm going to use the angles RCE, this guy right here in my given, my alternate interior angles, to prove that TR is parallel to CE. All right, and the only thing that proves lines are parallel is converse theorems. So this would be the alternate interior angles converse theorem. And then hopefully you notice what we've got, right? I've got parallel and congruent, right? And that was theorem number 5 from yesterday's notes that help us prove that things are parallelogram. So I'm going to use that to then say that RECT is a parallelogram, not a rectangle yet, just a parallelogram. Right, and I know this because if one pair opposite sides congruent and parallel, then parallelogram, right? Our little theorem from yesterday. All right, so we know he's a parallelogram. So all those 5 properties of parallelograms are holding true. Now we just need to prove that it is a rectangle. Okay, well, we haven't used our third given yet, that we have congruent triangles. Well, remember, anytime you have congruent triangles, you're probably going to be using CPCTC, right? So let's look at our 2 triangles, right? We've got, you don't have to do this, of course. All right, we've got this guy, right? That was our, let me scoochie him over. That's the orange one I have highlighted. And then we have the blue one, this guy. Right? These are our congruent triangles that we have highlighted up there in the picture, right? And so we already know that they're sharing, we know they're sharing the same base, right? So that doesn't really help me. We already know these sides are congruent. That's what helped us prove it was a parallelogram. So the parts that are really going to help me are going to be these hypotenuses, because the hypotenuses are the diagonals of the rectangle. If you notice that in the picture up there. So if the hypotenuses are the diagonals and these are congruent right triangles, well then the hypotenuses are congruent, right? So I'm going to use that little factoid that these triangles are congruent, then say, oh, well, okay, if the triangles are congruent, then hypotenuse TE is congruent to hypotenuse CR. And I know that because of CPCTC. All right. And so that is a major property of rectangles, is that they have congruent diagonals. Now, other shapes have congruent diagonals, right? For example, I'm getting a little ahead of myself, sorry, but isosceles trapezoids, they also, we're going to learn this tomorrow, they also have congruent diagonals. But I don't have to worry about that here because I've proven that he's a parallelogram that has congruent diagonals. And that means by process of elimination, he has to be a rectangle, right? So now I can just hop right to my proof statement. Oh, I could put these two guys together. So of course he's a rectangle because he's a parallelogram with congruent diagonals. Is a rectangle. And I know we didn't really write this down, but I'm going to write if parallelogram with congruent diagonals, right? I'm just basically writing that property down. If parallelogram with congruent diagonals, then rectangle. And I know that if-then statement was not in our notes, but again, we're using that property and kind of putting that together. And that's okay. All right, I'm so sorry. That video was extremely long and I kind of blurred my way through that. So again, feel free to kind of rewind and work through that as needed. And then you can get started on your assignment. All right, talk to you guys.